Electromagnetic radiation and astronomical observations, the wave properties of light. To begin our study of light, we're actually going to first discuss waves in general. For example, what happens when a pebble is thrown into a pond? As shown in the image here, where the pebble enters, the water starts to oscillate up and down. The pieces of water right next to where the pebble entered feel the water next to them going up and down, and they start to move up and down too. The disturbance in the water moves outward as more pieces of water start to move up and down. The water in each place only moved up and down, but a wave moved from where the pebble entered the water. So, no water moved outward. What moved outward is the disturbance in the pond surface. The outward motion of the disturbance transports energy from one place, the location where the pebble entered the water, to another, all points outward from the pebble entry point. This example illustrates that a wave is really a mechanism by which energy gets transported from one location to another. Furthermore, electric fields and magnetic fields can be disturbed in a similar way to the surface of a pond. When a stationary charged particle begins to vibrate, or more generally, if it is accelerated, the electric field that surrounds the particle becomes disturbed. Changing electric fields create magnetic fields. So, a moving charge creates a disturbance in both the electric field and magnetic field near the charge phenomenon. So, particle rather. The outward moving disturbance in the electromagnetic field is an electromagnetic wave. The phenomenon that we refer to as light is simply an electromagnetic wave. So, looking at the picture shown, light shown as a wave in graphic form, where the x-axis is the distance and the y-axis is displacement, and displaying how to calculate wavelength as the peak-to-peak distance. So, mathematically, the wavelength of light is usually referred to as letter I, or the Greek letter lambda. As you look at the picture, you can see the like a inverted letter Y. So, and that is referred to as wavelength, and the frequency is usually referred to with the letter F, or the Greek letter Nu, or as you can see, letter V, that referred to us as the amplitude. White light, for example, what comes out of a flashlight?
Is actually made up of many waves that each exhibit one of the different colors of light: red, orange, yellow, green, blue, and violet. The reason that different waves of light appear to be different colors of light is because the color of a light wave depends on its wavelength. For example, the wavelength of blue light is about 450 nanometers, while the wavelength of red light is about 700 nanometers. A light source that gives off white light is therefore emitting multiple waves of light with a wide range of wavelengths from 450 nanometers through 700 nanometers. All of these light waves move at the same speed, the speed of light. So you can determine their frequencies and see the red light has a lower frequency than the blue light. The wavelength of light can be extremely long or smaller than the nucleus of an atom. So, what do we call light that has a wavelength longer or shorter than a visible light that we are used to? Well, here is one of the example. Light that has a wavelength just longer than red is called infrared light. The next example is light with a wavelength just shorter than violet light, which is called ultraviolet light. The entire range of possible types of light, from the longest wavelengths or the radio waves to the shortest wavelengths, gamma rays, is called the electromagnetic spectrum. You may have learned in another course that light is peculiar in that it can be described, as we just did, as being a wave, but in some experiments it behaves and can be described more accurately as a particle. When we describe light as a particle, we'll refer to an individual packet of light as a photon. You can still refer to the wavelength and the frequency of the photon, even though you are considering it to be particle rather than a wave. If you go back to the very first discussion at the very beginning, we have tackled about how waves transport energy. So each photon of light does carry energy, and the amount of energy depends on the wavelength or frequency of the photon. The equation is. Now this equation is energy, H referred to as Planck's constant, and C is the speed of light. So moving on to spectra, if you have seen a rainbow in the sky, or if you have ever seen light pass through a prism and appear to emerge as a rainbow, you have seen a spectrum. What you have witnessed in either or these two cases is white light being dispersed. The different colors of light bend by different amounts when they pass through a glass prism or water droplets. That is, when white light passes through water droplets in our atmosphere. The waves of red light get bent by a different amount than the waves of blue light, so white light coming to you appears spread out into a rainbow.
In the blue straggler, in the blue straggler plot, wavelength or color where the intensity is near 1.0 means a lot of light was received by the source with this color. Have you seen the blue, the violet, the yellow, and the red ones? So, on the other hand, wavelengths there where the intensity is near zero point 0.0 receive very little light from the source with this color. The dips in the graph that fall to nearly zero correspond to the dark bands you see in the spectrum of the sun above. You will use the word spectrum interchangeably to refer to these two different representations of the dispersed light from an object, either an image or a two-dimensional plot, but in both cases, what we can determine is how much light with a specific wavelength was received from an object. So moving on to radio waves to gamma rays. When you use the term light, you are used to thinking of the light emitted by a bulb that you can sense with your eyes. Why we know consists of many wavelengths or colors of light from red to blue. When astronomers refer to these specific colors of light, they refer to this as the optical or visible portion of the electromagnetic spectrum. As I mentioned briefly before, radio waves are also light waves. Infrared radiation is a kind of light, usually abbreviation of IR. Thus, the same is true of ultraviolet waves or the UV, X-rays, and the gamma rays. These are all different kinds of light. The difference between these are types of light, and visible light is again the wavelength of the light. So what makes them different is the wavelength of light. Notice that the range that corresponds to the visible light we see with our eyes, optical range, is a very small part of the entire spectrum. David Helfand, an astronomer at Columbia University, makes an analogy between light of different wavelengths and sound of different octaves. There are two main points that should be emphasized about the different types of electromagnetic radiation, which is the radio, infrared, visible, ultraviolet, X-ray, and gamma ray. So first, the sequence from the longest wavelength, the radio waves, to shortest wavelength, the gamma rays, is also a sequence in energy from lowest energy to highest energy. Remember that waves transport energy from place to place. The energy carried by a radio wave is low, while the energy carried by a gamma ray is high. So, ganang baliktad siya. Like, second, different materials can block different types of light. More specifically, the Earth's atmosphere only allows certain wavelengths of light to penetrate to the surface. So much of the science astronomy deals with the study of how light is generated and emitted by a source, and what happens to the photons of light from the source as they travel from the source to a source, to a observer rather, and how the observer detects these photons. So let's consider the second of those 3 points, that what types of material can block photons of light from reaching us. If you consider only optical light, then you will probably say light can penetrate glass, air, and water, but light easily gets blocked by solids like plastics and metals, or perhaps the clouds in the sky. As this picture shown, you can see that Earth's atmosphere, which we usually think about transparent, is actually only transparent to certain wavelengths of light. This is illustrated in this cartoon or photo shown. So, all visible light penetrates the atmosphere. Most radio light penetrates the atmosphere, and some IR light passes through the atmosphere. We refer to the ranges of wavelengths in the spectrum that can pass through the atmosphere as a window. So, example, there is an IR window for light with wavelengths from 3.0 to 4.0 microns. So, 1 micron is equal to 1 million of a meter. So, in contrast, our atmosphere blocks most ultraviolet light and all X-rays and gamma rays from reaching the surface or of the Earth. So, because of this, astronomers can only study these kinds of light using detectors mounted on weather balloons, in rockets, or in Earth orbiting satellites. If you study the transparency of the Earth's atmosphere plot by the European Southern Observatory, you will see that you can represent this idea of windows in a more rigorous way. You can plot how opaque the atmosphere is, or equivalently, when percentage of photons are blocked by the atmosphere as a function of wavelength. So, for example, 0% of green photons are blocked by the Earth's atmosphere, but nearly 100% of all photons with wavelengths shorter than 100 nanometers are blocked from reaching the surface of the Earth.